So yesterday we talked about not vector value functions, functions of several variables. So the idea here, once again, is that we're going to have a function. The inputs, though, are going to be points. And we're going to stick to either points in the plane or points in space. And then we're going to have our process, and we're going to have an output, which are going to be real numbers. So once again, when they show you the temperature map, first thing, when they're looking at the weather, here's the temperature map. That's a function of two variables. They have the location in Ohio, and then they've got the temperature associated with it. Okay, so that's an example of a function of several variables. So yesterday we talked about the domains, the arithmetic, the graphs, basically all the basic stuff about these functions. And today we're going to start looking at the calculus of functions of several variables. And calculus means limit. So we'll talk about how, welcome in, Rick. We'll talk about how limits work. We'll have a chance to review how limits work from Calc 1. And then we'll see how this all gets fit together. So let's just wait. I think there's a couple more people trying to get in. Okay. All right, so warm-up question. What is the limit as x approaches a of f of x asking for? How does it relate to the limit as you come into the left, come into the right? So let's go back to first principles here back in calculus. You got yourself a function. You're going to graph the function y equals f of x. We're interested in some particular x value a. And when we look at the limit as x approaches a of f of x, what we're doing is we're sampling the function close to a to try to make a prediction about what's going to happen at a itself. So this is basically what we expect f of a to be by looking as x gets close to a. So the function is what we expect. So if that, or the limit rather, is what we expect. So if the limit is equal to L, then the picture we get from this is something like that. So as x gets closer and closer to a, without actually being at a itself, the function values, aka the y values, are getting closer and closer to L. What's actually happening at a, the limit doesn't care about. Okay, the limit doesn't care about. And there's a more precise definition that we'll talk about here later with epsilons and deltas, but we'll get to that when we get to that. So to answer the question, what's the difference between this and these two things? So if you're coming in and plugging in numbers a little less than a, this is what we mean by x approaching a from the left. And if we look at numbers coming in a little bit larger than a, this is what we mean by x approaching a from the right. In order for the limit to exist, what has to be true about the limits from either side? So if the limit as x approaches a of f of x equals L, what has to be true about the limits as you come in from each direction? Yeah, they have to be the same. They also have to both be L. Okay? So depending on what's going on with the function, sometimes you got to break it down and look at what's going on coming in to the left and what's going on coming in from the right and check to make sure those are the same. So let's take a look at this function here. So now we kind of got the idea of limit again. What's the domain of f? So looking at this function, you notice it's got a fraction. And for a fraction to work, the denominator can't be what? It can't be 0. So let's find out where the denominator is 0. And if you've got x squared plus y squared is 0, you can think of that loosely as a circle, quote unquote, centered at the origin with a radius of 0. This is only going to happen if both x and y are 0. So here's our domain. If we wanted to sketch it in the xy plane, we can certainly do that. Pretty much we're good everywhere except the origin. Okay? So this is what limits are built to do, right? Algebra is telling us we can't plug in 0, 0. We don't know what's happening at 0, 0. So we're going to use the limit to investigate what's happening near 0, 0. So it's natural to think about, okay, what is that trying to do? So thinking back to what limits were in Calc 1, when you had the limit as x approaches a of f of x, the input x's were getting close to, but not actually at, a. And we were looking at what the f of x values were doing. And we were looking to see if there was a pattern, if there was a trend, if we could make an educated guess about what the function should be doing at a by looking at x getting close to a. And on the real number line, there are two principal ways to get close to a. You can come in from the left or come in from the right. So that's the same kind of idea here. You follow? We don't know what's happening at the origin, but we can look at what's happening as the points get close to the origin. But herein lies a little bit of a challenge for us. All right. When we were on the real number line, we could approach a number from left and right. Okay? How many different ways are there to approach the origin? What are some ways you can get close to the origin? So you can come in from the left, you can come in from the right. How else could you get close to the origin? You can come in from, coming from the top, coming from the bottom. How else could you get close to the origin? Yeah, you come in on corners. You could come in really on any graph, right? You could come in along the graph of e to the minus 2x, inverse tangent of 7x. You could come in along that graph. There are infinitely many ways, you follow? So this is where, some people call this tricky. I call this is a richness. It's very rich. There's lots of different ways to come in here. And this is your first indication that there's going to be a lot of things that generalize from Calc 1. But we're going to have to be careful because not everything does, because there's a lot of different things happening here besides just the principal direction. So one of the big things we're going to be working towards is trying to figure out functions where if we just understand x and y, we'll understand everything. Okay, that's kind of, spoiler alert, that's kind of what differentiable ends up meaning later on. Okay, but for now, we've got a whole Pandora's box here of paths to choose. So this is where we investigate limits along paths. Okay, so let's look at our first example here. Investigate the limit along the following paths along the line y equals x. Okay, so this is how this works. Welcome in. So we're going to look at our function here. F of xy is 2y squared over x squared plus y squared. we want to look at the limit as xy approaches 0, 0. Oh yeah, no worries, Zeron. I know this is this is not my preferred way of doing this, but it gets the most people able to attend. So yeah, no worries. So we want to look at this limit, and we're going to go along the path y equals x. So once again, what does this mean? We're trying to get close to the origin. We're trying to figure out what's going on with the function here. And so here's one way to get close to the origin, coming down the diagonal there. Okay? So here's what we can do. The limit as xy approaches 0, 0 of f of xy, 2y squared over x squared plus y squared equals... What is going on with the tablet today? Equals, now we're going to come along the path y equals x. All right? So if we're coming along the path y equals x, that means I can substitute everywhere I see a y, I can substitute an x, or vice versa. But I'm going to sub in everywhere I see a y, I'm going to plug in an x. And then the pair xy goes to 0, 0 is equivalent, well, if x is going to 0, then y is going to 0. If y is going to 0, then x is going to 0. So once again, I'm going to take a problem involving two variables, and I'm going to impose a relationship between those two variables to turn this into a problem involving just one variable. Okay? So this is a classic concept we're going to be seeing over and over again. The way we try to investigate functions of two variables is looking at them, somehow getting it back to a problem involving one variable. Now what's going to happen here, folks? The numerator is going to be 2x squared. What's the denominator going to work out to be? Before we plug the limit in, Tim. X squared plus x squared is going to be what? So I'm going to have 2x squared over 2x squared. That completely simplifies to what? You follow? So along the path y equals x, the limit equals 1. Okay? Any questions on what's happening here? Where did they come up with this? They just told you. They said, just try along y equals x and see what's going on. All right? Let's look along the line y equals 2x. So I'm taking the limit as xy goes to 0, 0 of 2y squared over x squared plus y squared. And now we're going to go along the line y equals 2x. Okay, so once again we go over here and we think about what we're doing. I know I can't plug in 0, 0. So we're going to come into 0, 0 along the line y equals 2x. So sort of a different sort of diagonal line. So everywhere I see a y, I'm going to sub it in with a 2x. And once again, as x goes to 0 and x goes to 0 is going to automatically give you y going to 0. And y going to 0 is going to give you x goes to 0. So I can replace this limit of two variables with a limit of one variable along that path. And now I'm going to simplify. Don't forget, when you square the 2x, you've got to square the x and the 2. So you'd have 4x squared times 2, 8x squared. And the denominator, you'd have x squared plus 4x squared, which gives you 5x squared. And so when the dust settles and you do your do your canceling, what do you get for this limit? Eight fifths. Okay. So here's the question. Along one path we're getting 1, on another path we're getting 8 fifths. So what would you say is going on with the limit? Does it exist or not? Why or why not? What do you think? Yeah, the limit doesn't exist because we have two different paths with two different numbers. You follow? So once again, it's helpful to think back to Calc 1. If you had a situation in Calc 1 where coming from one direction you got 1 and from the other direction you got 8 fifths, you would say that limit doesn't exist, because in order to exist, the limit has to be the same from all directions. Okay? Now, here's where I love GeoGebra, because when I learned this, I could see the algebra, what was going on, but what was happening geometrically. That's where we talk about the lifts. So if we have a vector, if we have a parametric description of a curve, so this is a curve in the plane, then the lift to a surface is you take your x of t, y of t, so this would generate the curve in the plane, and then you look at f of x of t, y of t. And so this would lift the curve C to the graph z equals f of x, y. So let's see what's going on and to check what's going on graphically. And this is something on your next take home I'm going to ask you to do with GeoGebra. So here's the first thing you do is we're going to type in our function f of x, y, and that's 2y squared divided by x squared plus y squared. Oh, wait a minute. We got to be in 3D for this. So f of x, y is 2y squared over x squared plus y squared. And now we want to enter our path. So the first path we had was y equals x. So we had y equals x. And remember, we can do the cheap parameterization for this. We could let x equals t, and if x is t, then y would also be t. So that would be how we graph that line in the plane. So if we just put in here t comma t, then sure enough, we've got that line in the plane. And so once again, we want to arrange it with positive x and positive y. Okay, there's our diagonal y equals x. Now what we want to do is we want to lift that curve up to the surface to try to see what's happening with the function values, aka the z values. So I'm going to do f of t comma, excuse me, not f, but I'm going to do a parametric, so I'll use parentheses. X is t, y is t, and the z will be f of t comma t. All right. Now, when you lift it to the surface, you can see there it is on the surface. You've got a line, and it's heading into 1. If we can zoom in a little bit here, it's going straight into 1. So that's the lift to the surface, and notice it's a line on the surface as well. Okay, so there's that. And we can go in and change stuff. If y equals 2x, then x is t. X is t, y is 2t. So we can change that. So we'll put a 2 here. And we'll put a 2 here and a 2 here. And then you can see that it's going into something that's not 1. You follow? So it's something, but once again, it still looks like a line. But you don't need to restrict yourself. You can pick any curve that goes through the origin. So, for example, if you wanted to go along the parabola y equals x squared, you can certainly do that. So you can see here, let me get it organized. So once again, in the xy plane, you've got yourself that parabola. And here's what it looks like. Now, based on this, when you lift the curve to the surface, what happens to it? It looks like the parabola dips down. It appears as if the limit along the parabola would be what? Can you see? If I turn it this way. As we come in on the parabola, the z values are getting closer to what here? Yeah, it looks like you're getting closer to 0. And you could actually try that out. So we've already convinced ourselves the limit doesn't exist. But just to do one more of these here, if I take the limit as xy approaches 0, 0, of 2y squared over x squared plus y squared, if we go along y equals x squared, once again, y goes to 0 means x goes to 0 and vice versa. So this would be equivalent to x itself going to 0. You'd have 2x to the 4th over x squared plus x to the 4th. And we could factor an x squared out of the denominator. And get a little cancellation. So as x goes to 0, we've got 2x squared in the numerator going to 0. We've got 1 plus x squared going to 1 in the denominator. And sure enough, that's 0. Okay. So once again, by using the concept of the lift, you can look at what's happening along all these different paths. And and I encourage you to play around with it, right? Try, have some fun with it. Like, what's your favorite curve that goes through the origin? What's your favorite trig curve that goes through the origin? Let me ask you that. Your favorite trig, the only wrong answer would be a curve that doesn't go through the origin. So what's your favorite trigonometric function that goes through the origin? Yeah, sine. Sine's a good one. And then we just put that in there. And then we would have sine t. Sine t. There it is. And so there's the sine wave sitting there in the plane, and we're lifting it up to the surface, and it looks like it's going through what? If you had to, I mean, it's hard to see, I understand, but looks like it's going to 1. You follow? And you could fire it up and see what happens. Okay. You'd have sine squared over x squared plus sine squared. Might be a good candidate for some L'Hopital, right? Do some L'Hopital on that and get it to 1. All right. But once again, when you're looking at a limit as you approach a point in the plane, I mean, you have to consider all the paths. And so this is what motivates the formal definition. Okay, so here's a big recall. Recall the limit as x approaches a of f of x equals L means given epsilon greater than 0, there's a delta greater than 0, so that if the absolute value of x minus a is between 0 and delta, then the absolute value of f of x minus L is less than epsilon. So let's talk about this again, because it might have been a while. You might have seen this a little in Calc 2 when you did like limits of sequences. I know that I bring it up. You might remember back to when we talked about limits of vector valued functions, we talked about it, but this is sort of the story that's worth repeating. Remember, what you want to remember about is when you look at the absolute value of the difference u minus v of real numbers, this is the distance between u and v. So what's this definition talking about again? So we got our function here. Here's our function y equals f of x. We're looking near the point x equals a. We're claiming that the limit is L. X's are getting close to a. F of x's are getting close to L, but the y's are the f of x's, so we're looking at the y's getting close to L. So here's the setup. So to actually prove this is the case, we have to show that we can get the y values as close as we want to L by getting the x values close enough to a. So how close is close? Well, what we do is we let epsilon be the error here in the outputs. So we think of epsilon, think of that as an error. That's how far away from L we're allowing the outputs to be. And what that'll do is that'll set up a little window around A. So delta is how close we have to be to A without actually being at A, because we don't care about that, to guarantee that the outputs are within epsilon units of L. Okay, so the way we get closer and the way we get the function closer and closer to L is by getting the x's closer and closer to A. So that's the epsilon delta definition of limit. It has to do with distance between outputs coming from distance between inputs. That's the whole idea. So this is our distance between inputs, and this is our distance between outputs. All right. So let's take this up a dimension. So once again, I encourage you, maybe you want to go back, to section, well, it was at the end of 14.1. Vector valued functions, when we looked at the limit definition, this very definition, and we vectorized it. And now what we're going to do is we're going to generalize this definition to this. Okay, so once again, given epsilon greater than 0, there is a delta. So epsilon is serving the same role it did in the last two definitions of limit we had. Epsilon is your error. It's your allowable tolerance in the outputs. Delta is playing the same role as it's done in the last couple of definitions. Delta is your distance between the inputs. In this particular case, the inputs are points. And how do we measure the distance between points? That's your distance formula in the plane, which once again is courtesy of the Pythagorean theorem. So given epsilon greater than 0, there's a delta greater than 0, so that if the points x, y are within delta units of the point AB. So this is saying if, oops, I should do this in blue just to be consistent with the colors here. So, oops, blue. So blue's for inputs. So this is saying that the distance between the inputs from x, y to AB is less than delta. That's what that's saying. Then look at the outputs. We didn't change this at all. Why? Because the outputs from this function are real numbers, just like the outputs from this function are real numbers. So this is the distance from the output f of x, y to L. But it's the same concept. We're getting the distance between the outputs small by getting the distance from the inputs small enough. And no matter how close you want the outputs to be to L, you can figure that out. You can find a distance close enough to AB to make that happen. Now here's a picture from the OpenStax book of what's happening. Notice here the z-axis, these are real numbers. So here's your L plus epsilon, here's your L minus epsilon. So we're setting up an interval on the z-axis. We're looking at real numbers here. And so it's literally an interval from L minus epsilon to L plus epsilon. What's being set up here in the plane is we've got our this inequality. If we square both sides, hopefully we can recognize this as a little disk. Okay? So we don't actually have the boundary of the disk. We don't actually have the circle here. This would be sort of a dashed boundary, and we don't include the center AB itself. But so in other words, if you want to look at this just in 2 dimensions here, right? This is what we would look at. So in the business, we would call this a punctured open disk. Punctured means that we remove the center. So if you get like a hole punch, you just punch out the center. Open means it does not include its boundary circle. These are technical topology terms, but that's kind of what we're looking at. Okay. So something you should do in the privacy of your own home is to look at this definition, study this picture, and see how this is just one dimension up of what we had back in Calc 1. So in other words, if you take this picture and this story from your Calc 1 class or your AP Calc class, and you bumped up the dimension of the inputs, this is the picture you'd get. Part of the big story in Calc 3 is to show you how it's the same concept, whether it's vector valued function limit or function of several variables limit. It's the same concept in both classes. So here's our 2-path test. So this is like what we saw here. If 2 paths produce different values for the limit, then the limit doesn't exist. So if you go along one path and get 1, and you go along another path and get 8/5, the limit plain out doesn't exist. Okay? On the other hand, if 2 paths produce the same value, the limit may or may not exist. So if in the 2 paths we did earlier, we looked at y equals x and y equals 2x, if both of those went to 1, well, that just means that those 2 paths give you the same limit. There's still infinitely many other paths we have to check. So let's look at example 2 to kind of hammer this home. Let's look at the limit as xy approaches 0, 0 of 2y cubed over x squared plus y squared. And they want us to go along the path y equals mx. So by doing this, what we're looking at is we're sort of at one fell swoop here. We're looking at all the different paths coming into the origin, except for the y-axis, because there's no slope there. But any line through the origin, any non-vertical line through the origin is going to get captured by this. So I'm going to plug in everywhere I see a y in mx. And if y goes to 0, x goes to 0, and if x goes to 0, y goes to 0. So xy going to the origin can be replaced with x going to 0. the numerator, we cube the m and the x. In the denominator, we square the m and the x. We get a 0 over 0 situation, which means that the factor theorem says we should be able to factor. And sure enough, we get some cancellation here. As x races off to 0, the numerator goes to 2m cubed times 0. The denominator is 1 plus m squared. No matter what that slope is, whether it's positive or negative or 0, when you square it and add to 1, you're going to get a number 1 or bigger. So this is just going to go to 1 plus m squared, a non-zero number, and sure enough, we get 0. So regardless of what's happening, regardless of what line you pick, y equals mx, when you come into 0, you're going to get 0. Is this enough to prove that the limit is 0? No, because maybe it screws up on an inverse tangent. You follow? So the answer here is no, because there are more paths to check. So what do we do if this happens, right? If we get two paths and we get different numbers, then we're done. The limit doesn't exist and we move on. If we're getting the same number, then we have more work to do. And so we have the formal definition to go from, or we can use some limit properties to help us. But let's go through this. Now, on your next take home, there's going to be one like this. But what I do is I just have you fill in the explanation for each step. I don't have you try to create it out of the ether. But let's see. So let's look at let's just go through this and make sure we understand the reasoning behind the steps. So we got to prove this is 0 using the definition of limit, because in the definition of limit it has to do with distances. So it's not going to matter how we get to the point AB, because as soon as we're in this small little disk around AB, as soon as that curve gets within that disk, we're going to be guaranteed that the function values are within epsilon units of our target limit. So, I don't know what sort of practice you've had with epsilon delta back in your early calc days, but typically what we do is we start off with what we want. We want the f of xy minus L to be less than epsilon, and we work with this inequality. So we want 2y cubed over x squared plus y squared minus 0 to be less than epsilon. And then what we look for is we look for the distance to the origin to be less than, I'll write it down here, delta. So we're looking for, how do we got to find our delta somehow. So in this case, we're looking for this to show up. But we can simplify this. All right, so we're looking for this to happen, or we're looking for this to happen. Right? So we're looking for getting x squared plus y squared, I guess, to help us figure out what our delta is. So we're going to start with this inequality, and we're going to do some algebra and see if we can get this stuff to pop out. Let's look at the absolute value of 2y cubed over x squared plus y squared. We're subtracting 0, so that's just the same. So now let's start looking at some properties here. So using properties of absolute values work well with multiplication and division. If you think of it constructively, absolute value is just going to make things positive if they're not. So if you've got two numbers and you're dividing them, you can either divide them and then make the answer positive, or you can just make the numerator and denominator positive to begin with and then divide. The absolute value works well with multiplication for the same reason. You can multiply two numbers and then make them positive, or make the two factors positive and then multiply them. Now, what about the denominator? Do I need absolute values here? No. X squared plus y squared is always going to be 0 or bigger. And since we're actually going into the origin as a limit, we're not actually considering the 0 case. So I don't really need absolute values here. And I don't need absolute values around the 2. Okay. And I don't need the absolute values around all of the y cubed. I can write y cubed as y squared times y. And use the product rule. And then I can drop the absolute values around the y squared, because y squared is always positive. So I've got the absolute value of 2y cubed over x squared plus y squared minus 0 equals, so we've got it down to this now, 2y squared, where did it go? I lost it. We've got 2y squared absolute value y over x squared plus y squared. And remember, what the goal is here is I want to make this small. I want this to be less than epsilon. Okay, so let's check this out. So now here's what I'm going to do. I'm going to say, well, you know what? This is going to be less than or equal to 2 absolute value y over x squared plus y squared. Okay, so the 2 absolute value y, period. So the question is, wait a minute, what happened to all of this? Well, that kind of got hidden into here. Because if I look at y squared over x squared plus y squared, I've got the same, I've got a y squared and a y squared. And if I think of this fraction, the numerator is always what compared to the denominator? Yeah, it's always smaller, because I've got the same thing here, y squared, but I'm adding some positive number to it. So once again, this is going to be less than or equal to 1, since x squared plus y squared is always going to be bigger than or equal to y squared. Does that make sense? So now I can write this as 2 square root of y squared, which in turn is less than or equal to 2 square root of x squared plus y squared. So I'm just replacing the absolute value of y with the square root of y squared. And here I'm just replacing what's underneath the radical with something that's potentially bigger than it. Once again, by adding an x squared. So both of these inequalities come from the fact that x squared is going to be bigger than or equal to 0. If x squared is bigger than or equal to 0, that makes the denominator of this fraction bigger than or equal to the numerator, which makes the fraction less than or equal to 1. It makes the radicand here bigger than or equal to the radicand here, which gives us that inequality. And why do I care about this? This is what I'm on the lookout for, because this is what I want less than delta. Yeah, exactly. Okay. So to kind of put all this together, my f of xy minus L was equal to the absolute value of 2y cubed over x squared plus y squared, which through a series of algebra I've shown is less than or equal to 2 times the square root of x squared plus y squared. So if I force this, if I make this less than epsilon, then my original thing will be less than epsilon. So I'm going to choose delta to be epsilon divided by 2. So I would divide both sides by 2 here to figure out what the delta should be. And if 0 is less than the absolute value of x squared plus y squared is less than epsilon over 2, then the absolute value of f of xy minus L, which is less than or equal to 2 times this, will be less than 2 times epsilon over 2, which is equal to epsilon. Now, I'm not sure how much epsilon delta shenanigans you did back in your earlier calculus. Typically at Lakeland, I have students do a proof with a linear function, scratch work informal proof, and in class we do a quadratic or two to show how that gets a little trickier. But as you can see in here, it's more about inequalities and bounding than straight up calculations. All right. So on the next take home, I've got one of these on there, and I go through the steps, and you just have to justify, well, why did this happen? Where did this go? You follow? So it'll be there. The skeleton will be there. You just have to fill in your justification. Okay? But big picture, what does this mean? This says that I can get this function as close as I want to 0 by getting the inputs x, y close enough to the origin. If you want to be within epsilon units on the z-axis, you just have to be within epsilon over 2 units in the plane. So if you go back to this picture, because I'm not going to attempt to sketch this. So what we've shown is that our delta here is epsilon over 2. So if you wanted to be within half a unit on the z-axis, then you would set up your disk about the origin to be a quarter unit. All right? No matter what your epsilon is, you can get close enough. And it doesn't matter what path you choose then, because no matter what path you choose to get to the origin, you're going to eventually have to come within this circle. You follow? And so by setting up the epsilon delta, you take care of all the different paths. All right. Well, that's more than enough for today. We'll stop here today. Tomorrow we're going to do more with limits. We'll talk about limit properties. A lot of the stuff is going to carry over from Calc 1, because even though the epsilon delta thing is kind of cantankerous, and I'm cantankerous, I'm an old man, it does provide the same architecture to prove all the limit laws that we had before. So as always, folks, thanks for tuning in. I really do appreciate it. Thanks for the participation and the questions. And I hope to see most of you tomorrow.